and welcome back. So in our previous segment, we were talking about the magnetic field of the sun. So now we are going to use that in order to explain what sunspots are. So in this picture here, this shows the surface of the sun, and you see all of those little black dots on it. So those black dots are going to be sunspots. So let's talk about what they are. So a sunspot, they have a 22-year cycle. So this means that at year 1 of the sunspot cycle, the sun has no sunspots on it. Okay? And then as the years go by, more and more sunspots begin to appear on the surface of the sun. And then all of a sudden the sunspots begin to go away. Now that is going to be year 11 in the sunspot cycle. Then the sunspots begin to come back. Okay, they become more numerous on the surface of the sun, and then they start to disappear again. And then once they've all disappeared, that's going to be year 22. And then it starts all over again, and so sunspots begin to appear, and then they disappear. So you might be wondering, why does it have like 2 mini cycles to the 22-year cycle? So I'll explain that to you here in just a moment. So what are sunspots? They are places where the magnetic field is coming out of the sun and going back into the sun. So I have here a coffee cup, okay, and you see that the coffee cup has a handle. So let's pretend that this is the surface of the sun, and here's the magnetic field where it's coming out of the sun and then where it's going back in. So you'd have a sunspot here, and you'd have a sunspot over here. So sunspots always come in groups of 2. The place where the magnetic field comes out and the place where the magnetic field goes back in. So why do sunspots look dark? So they appear as black dots on the surface of the sun, but it turns out that they are actually very, very bright. Okay, they are at a temperature of 3,800 Kelvin. That's the temperature of a sunspot. That is blindingly bright. So if you recall, back in Unit 1, we had these things that were called the black body radiation laws, and there was a formula that, sorry about that, so F is equal to sigma T to the 4th. So this was the energy output, so this is the energy density, F, and it was equal to a constant, and then the temperature raised to the 4th power. So that the greater the temperature, the brighter an object is going to be. So these things are at a temperature of 3,800 Kelvin, so they're so hot that they would produce a blinding light that you could not look at. It'd be like trying to look into a welder's torch. So why are they going to be dark? Okay, it's because the surrounding material is so much hotter. So the yellow part of the sun is at about 5,800 Kelvin, which means that's at a higher temperature, which means it's going to give off more energy, so it's going to be brighter. And it's so much brighter, it makes these sunspots look like they're black when they're really not. So the question now is, well, why would a sunspot be cooler than the surrounding material? Okay, the magnetic field traps the energy. So the energy underneath the sunspot, that's in the convective zone, is coming up to the surface. And so the magnetic field on top of it holds that energy in like a lid. And so that means that the energy can get out over here in the yellow part, and the energy can get out over here, but it can't get out here. So that means that the sunspot's going to be cooler than the surrounding material. Okay, now let's talk about how do sunspots form. Now, it's really a lot easier if you watch this video rather than just trying to look at those pictures. So see if you can find this video on the internet. So it's magnetic field lines of the sun. So I think if you just type in magnetic field twisted of the sun, you'll probably find this video. Okay, and so what it's going to show is that initially the magnetic field of the sun is going to come out and then go back around, comes out and it goes back around. So just your standard magnetic field, just like the magnetic field of the Earth. Okay, but the sun is rotating. Because the sun is a gas, that means that at different latitudes, so these are the latitudes of the sun, the gas is going to be moving at different speeds. So if you want an explanation for that, down at the bottom of the PowerPoint there is where I try to explain how that can occur. So it's kind of complex, but just know that at different latitudes, the gases are moving at different speeds. So we call that differential rotation. The equator is going to rotate faster than what the North Pole is going to be. So initially, you got your magnetic field that's going to be straight up and down, but do you notice that it's being bent, it's being stretched out sideways, so that eventually the magnetic field is going to wrap around the sun, and instead of being up and down, the magnetic field is going to be going like this. So it's going to be going sideways around the sun. Okay, now the next thing that's going to happen is inside the sun, you got all this energy that's coming up from the convective zone. And so what it's going to do is it's going to make the magnetic field bulge outward. So here is, let's pretend that here's the magnetic field and it's going sideways. Okay, and because of the heat that's coming up, can you see that it would cause that magnetic field to bulge up and out of the sun? So then you're going to have one place where the magnetic field goes in, and you're going to have one place where the magnetic field comes out. And that's going to be your sunspot. So now we've explained how do we make our sunspots. Now the question is, why do they go away? Okay, so what's going to happen is the sunspots, as more and more of them form on the surface of the sun, they're going to get crowded together. And so here's a picture of a sunspot up here at a northern latitude, and here's a sunspot below it at a lower latitude. And you'll notice that they're reversed. And that just turns out that when you wrap this thing around, the magnetic field will be going this way, and then underneath it, the other magnetic field will be going in the opposite direction. So as the south pole of one of the sunspots gets closer to the north pole of the other sunspot, eventually they get sucked together. Opposites attract. And when they come together, they'll cancel each other out. So these sunspots will begin to cancel each other out at the end of this 11-year cycle. But what happens, though, is after they have canceled each other out, north has become south and south has become north. So it used to be that this was the north magnetic pole and this was the south magnetic pole. But at the end of this cycle, at the end of this 11-year cycle, this is south up here and this is north here. Kind of weird. And then it starts all over again, and at the end of that 11-year cycle, north is north, south is south, and then we're at 22 years. So that's the reason why we said that we had like 2 mini cycles inside of this 22-year cycle. Okay, let's take a break, and when we come back, we're going to talk about what a prominence is and what a solar flare is.